Hello, Chemistry of Earth and Space Science. Here we are finally on the last video of Lesson 2, all about the chemical reaction types. So the last one, we've done synthesis, we've done decomposition, we've done single replacement. Single replacement has an activity series that tells us whether the reaction is going to occur or not. Well, we have something that's going to do the same thing here and tell us whether the reaction is going to occur or not, also with double replacement reactions. So in a double replacement reaction, you have two compounds. They're almost always dissolved in water. And when they're dissolved in water, they both have a clear color. Maybe it might be a clear blue color, a clear green color, a clear red color, but they'll be clear, be able to see through. There'll be no solids in there. And when they react together, sometimes, not all the time, they will exchange their metals, take the cations and swap them out. So if I had A, B, and C, D, and I mixed them together and this reaction actually occurred, the A and the C would swap places, and I would get AD, and I get CB. So the example might be silver chloride reacting with, sodium chloride reacting with silver nitrate, and when sodium chloride reacts with silver nitrate, the sodium and the silver will swap places, and I will get silver chloride and sodium nitrate. Okay. That reaction will occur. That reaction will occur. So when writing a double replacement reaction, you do the same thing. You kind of write all the reactants. Here we're going to use this example. Lead 2 nitrate reacts with potassium iodide solution. So we've got two solutions, both dissolved in water. We're going to start with the reactants. We've got lead nitrate, and we got potassium iodide. Next thing we do, we're going to predict our products. So let's have that lead and that potassium switch places. Cation replaces cation, or metal replaces metal. Like dissolves like. We saw that back in the water chapter, toxic tides. So the lead switches places with the potassium, and when they switch places, you get lead iodide and potassium nitrate. Now, lead is going to, over here on the left-hand side, was lead plus 2, it says lead 2, and over here it's going to stay lead 2. So if that's lead 2 and iodide, we need to have a 2 on that iodide. Now, it's not balanced. We'll worry about that later because that's not that big of a deal here. Just making sure that the cations swap, and when you're writing the formulas, the cations are listed first. Now we have to figure out whether this reaction is actually going to occur. So not every double replacement reaction will occur. Some will just mix together and nothing will happen, and some will form precipitates or maybe gases or something like that. So we have this reaction, which we have, and we're going to say, well, let's figure out whether or not the reaction is going to occur. So we're going to do that using what's called a solubility rules. So not every double replacement reaction is going to work. In order for them to work, they either have to form a gas or a precipitate. We're going to focus mostly on precipitates here. Precipitate is when two ions come together and they form something that is not able to be dissolved in water, and they fall out of solution. They become a solid that falls to the bottom of the container. So when you have a double replacement reaction, another term for them, the fancy ones, is to call a precipitation reaction. So here's a model to show how it works. So suppose I have my lead nitrate solution, there it is on the left-hand side, and my potassium iodide. And when I dump everything into the container, the nitrates do nothing. They just get in double the volume. And same thing with the potassiums. They do nothing. They just double the volume. In the beginning, lead nitrate is an ionic compound. All the ions are floating around independently. Secondly, the Ki, potassium iodide, is also. It's dissolving in water. But then when they come together, the ions come together, and the leads and the iodides, when they come in contact with one another, they form a precipitate. That would be what we would see. We would see a precipitate being formed. Clear solution mixed with clear solution, and you get this really cool bright yellow precipitate for this reaction. Because the potassium and the nitrate are going to stay soluble, nothing happens with those. They were in the smaller container to begin with. They go to the other container, and absolutely nothing happens. Sometimes, if there's no precipitate, you're just literally just mixing everything together. So here's a picture of that lead nitrate solution. So you had two clear liquids. One was in a beaker, and then the one was in the top beaker, and they mixed them together, and you got this yellow precipitate. Well, when one mixes the ions, and they form a compound that is, the word we're going to use is insoluble, then you have a precipitate form. So we're going to go over what are called the solubility guidelines or solubility rules. One of the compounds that's on a product side has to be a precipitate for a double replacement reaction to occur. I'm going to say that again. One or both of the products in a double replacement reaction have to be a precipitate for this reaction to occur, especially when talking about precipitation reactions. So the precipitate is literally a insoluble solid, or maybe a insoluble gas. That's where you would see bubbles. In the case of our acid-base neutralization, which was just a fancy double replacement reaction, maybe that thing that's formed is water. So here's the solubility guidelines, and let's interpret this. So there's two different sets. There's this set which says soluble, and this set says insoluble. And what it does is lists a whole bunch of ions that are pretty common ions, and telling you, as far as this one goes, this table goes, everything on here is soluble, except you see those little exceptions at the bottom. So any salt, any ionic compound that has group 1, lithium, sodium, potassium, rubidium, cesium, any group 1 ion metal, or it starts with NH4, that solution, regardless of what the anion is going to be soluble. It's going to dissolve in water. If the anion is nitrate or acetate or chlorate or perchlorate, then those also will always be soluble in water. The halogens, chlorine, bromine, iodine, they have a tendency to be soluble, but when they have these heavy metals, the silver, the mercury, the lead, as their counterpoint, then when they are dissolved in water, you'll see, like, say, for instance, lead chloride or lead iodide. That was an example with the yellow precipitate. That yellow precipitate was lead iodide. Iodides are usually soluble, except lead is one of the exceptions. So what happens? The lead iodide forms a precipitate. So these exceptions on this list, are the times when those anions will be insoluble. So those are going to be forming the precipitates. You see, we got chlorine, bromine, iodine, and also sulfate. Sulfate is almost always soluble. But again, the heavy metals of silver, mercury, and lead, but they've also added calcium, strontium, and barium as ones where they would also be insoluble. The second set that I have here has these things that are insoluble. So what this says is these anions and cations. I see a terrible spacing here. I'm going to fix that because it's going to drive me crazy. Give me 1 second to fix a slide. No, I shouldn't do this with the video, but what the heck. Wrong one. Well, I guess I got to stick with it. I really can't find the video. Oh, here it is. Okay. We'll go down here. Doink, doink. Doink. There we go. I don't like these spacings. Okay. So back to the show. So these are all insoluble. So anything that ends in a sulfide is going to be insoluble. Anything that has a chromate as its anion is going to be insoluble. Anything with carbonate is going to be insoluble. Anything with phosphate is going to be insoluble. The exceptions here are the times when these anions are going to be soluble. You see, these exceptions are the exceptions to the insoluble rule. So if I had magnesium sulfide, that would dissolve in water. But if I had, say, cobalt sulfide, that would not dissolve in water. Iron sulfide, that would not dissolve in water. Osmium sulfide would not dissolve in water. But again, group 1, say sodium sulfide, would dissolve in water. These exceptions are when they are soluble. What I don't like about this list, but it's what was put in the PowerPoint, notice that the next three, chromates, carbonates, and phosphates, are all insoluble except for something we already mentioned in the last slide. That's the fact that on the last slide, we said that group 1 and ammonia cations are always going to be soluble, no matter what they're paired up with. So this is kind of redundant, the chromate, the carbonate, and the phosphate. And then there's hydroxide, which also has the same kind of rule. Ammonia and group 1, but also they add calcium, strontium, and barium. These are situations where calcium hydroxide would be soluble, strontium hydroxide would be soluble, barium hydroxide would be soluble. So your solubility guidelines might look a little like this. Oh, wait, I skipped over it. There will be a solubility guidelines in your packet, which will look a little different than what I just went over, where it just describes all the ions and whether they're soluble or not and what the exceptions are. So let's look at the list. Strontium sulfate. Strontium sulfate, is that going to be soluble? Let's see. So if I do this, if I go back to my solubility guidelines, like strontium and sulfate, strontium and sulfate. So I'm going to go back to my list. There's sulfate, and notice that strontium is one of the exceptions of sulfates being soluble. So in this situation, our strontium sulfate would not be soluble. What about sodium nitrate? Well, I can tell you right now, just because I've done this enough, sodium nitrate is going to be soluble. But why? Let's go back. Two reasons. One, group 1, anything that starts with group 1 is going to be soluble. Sodium's in group 1. Or it's a nitrate. This has like the double whammy. It has group 1 cation and nitrate. This thing is going to be, I don't want to call it super soluble, but this is going to be definitely a very soluble solution. This will not form, that precipitate will not form. So we get soluble. And then lead chloride. Again, let's go back to our list. You'll get familiar with the list, hopefully. Chlorides. Chlorides are soluble. Yay, it's soluble. But wait, lead is one of the exceptions. So lead chloride would be insoluble. And I just did that. I didn't want to do that. So lead chloride is going to be insoluble or not soluble. So let's look at the double replacement reaction. You write the reaction. You write the reactants. You write the products, like we did. Switch has metals. But then, when writing the cation first, blah, 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 we have to check the solubility rules to see if either one of these compounds is insoluble. Either one of these is insoluble. So we go back to our solubility rules. Let's see. Iodide, lead iodide is going to be insoluble. Lead iodide is going to be insoluble, so this is going to form a precipitate. So that lead iodide is a solid. What about potassium nitrate? Is that going to form a solid? Uh-oh, potassium is in group 1. No way. And it's potassium with nitrate. Double whammy, potassium nitrate is not going to form a solid. It is going to be soluble. It is not going to form a solid, not form a precipitate. Those potassiums and the iodides will just stay in solution. Okay, let's try example. So say we have this reaction, which we have a solution of copper 2 chloride mixing with lead acetate. See how well my pen is going to work today. You going to cooperate today, pen? Okay, wish me luck. Okay, so we have copper, 2 chloride, plus lead, 2, oops, did a whammy. I don't know what makes it do that. Maybe it's just a part of my tablet that's not in great shape. Let's try that again. There we go. Where's my cursor? 2. And acetate is C2H3O. Gosh. It's going to be a day. I can tell already. Wink, wink. Okay. Try it again. H3O2 has a -1 charge, so I need 2 of those. Now, what are my products going to be? Well, my cations have to switch places, so the lead is going to switch places with the copper. So down here, I'm going to write down here because there's space there. The copper at +2 is now going to pair up with the acetate. And the lead is going to pair up with the chloride. Okay, so we have to ask ourselves, is this compounds, either one of these products, going to be soluble or insoluble? So we go back to our solubility rules. I see copper acetate. So, acetates are always soluble. Acetates are always soluble right here. Acetates are always soluble. Acetates are soluble, soluble, soluble. So that one's going to be soluble. Okay, let's try the other one. What was the other one? Is lead chloride. Okay, let's see. We don't have a lead rule, but we do have a chloride rule. Chlorides are soluble except, and lead is one of the exceptions. So that means that that ion, that compound of lead chloride is going to be a precipitate, and you get the reaction to occur. Okay. I'm going to go ahead and quickly put another slide in here so I can adjust. Let's see. I'm going to duplicate this slide. Okay, so here's the second reaction. It said sodium carbonate, let's see, Na, carbonate, CO3, 2 minus, need 2 of those, plus calcium chloride, calcium chloride, makes, now let's swap our cations, sodium and the chloride, sodium and the calcium. So now I have sodium is now with the chloride, and my calcium, I'm so close. The calcium is now with the carbonate. Maybe I'm just moving too fast. doesn't like me doing that. I'll try to slow down. CO3, that didn't work. Okay. Now we go back to our solubility rules and see whether sodium chloride is soluble and see whether or not the calcium carbonate is soluble. So I remember that group 1 is always soluble, and sodium is in group 1, so I know that the sodium chloride is not going to be soluble. What about calcium carbonate? Let's see. I remember there was a carbonate rule. Is it here? No, it wasn't that one. Let's see. Well, there it is. Carbonates. Carbonates are insoluble except for ammonia and group 1. And right now we have calcium carbonate, right? We have calcium carbonate. Calcium carbonate is going to be insoluble. So this is my precipitate, and this reaction would occur. So your practice for this is two pages. One of them is the solubility rule practice, getting used to the solubility rules and how to read them. I can just say this: if something is not listed as being soluble, then it's not. So there's no rule for it. So for instance, there's no rule for vanadium and bicarbonate. So vanadium bicarbonate, considering there's no solubility rule for it, sodium bicarbonate would be insoluble. And then a series of double replacement reactions. We have to determine whether or not what the products are, and also what is the precipitate. So that's all I have for lesson 2. I hope to get these out early tomorrow into YouTube and into your Schoology classroom. Until then, toodles.